Just a heads up, some of my slides are going to have code on the sides of the screen. If anyone wants to scoot in early on, now would be the time to do so. Yeah, great, I'll leave a minute here. Cool, so it's really great to be here. My name is Leland Richardson. As Jason said, I work at Google. I work on the Android UI Toolkit team on a project called Jetpack Compose. So, show of hands, who here has actually heard of Jetpack Compose? Okay, some people. So let's dive in and say, okay, what is Compose? So first and foremost, Compose is a declarative UI runtime. It's a component-based UI framework, much like React. In fact, many of the APIs were inspired by React and other frameworks that you're probably familiar with. It's a Kotlin compiler plugin as well. So we do some compile time optimizations, and we actually plug directly into the Kotlin compiler. And so that means that if you want to use Jetpack Compose, you do need to write your code in Kotlin. And Kotlin, if you're not familiar with it, is the language that you can use for Android. Android is now a Kotlin-first platform. And Jetpack Compose is built by Google. It's built by the Android UI Toolkit team themselves. So this is the same people that maintain Vue.java, for instance. Now, Compose is sort of like three parts. There's the runtime, there's the compiler, and then there's also what we call Compose UI. And Compose UI is a complete ground-up rewrite of the Android UI Toolkit. And so this means that the entire UI framework that you think of when you think of Android is sort of actively being rewritten on top of this new programming model and runtime. This is a really big undertaking, but I'm actually not going to be talking much about this today, and I'm mostly going to be focusing on the runtime and how it works and what that might mean to you. So Compose UI and the runtime and everything else is completely unbundled from the underlying Android operating system. We do this for several reasons, but a big one is just so that we can actually iterate on things and release new features, and so people like you don't have to wait for phone manufacturers or anything like that to upgrade the operating system. It's just a user space library. And it's also open source. So as of Google I/O, we started working on this in the open. And so you can go and kind of see what we're working on, how things work if you really want to dive into it, contribute, any of that. But the kicker is it's really not ready to use yet. It's not even alpha, it's pre-alpha. So if, look at this talk as me just sort of talking about it and sort of things that I find interesting and I think you might find interesting, not trying to sell it to you right now as like a thing to actually use. So obviously I'm pretty excited about this. I work on it, but here I am at a React conference and I'm talking about this Android thing. And some of you might be like, well, why is he here talking about this? How is this actually relevant to me? And that might be a fair question. I assume some people in the audience might be Android developers, maybe in a past life, things like that. But I think really I just want us to take a step back and really look at the mobile UI development landscape right now. And some of you might be aware that recently Apple released Swift UI. And so this is pretty interesting. What we're starting to see just in the last couple of months is that like 3 of the world's largest companies are investing a ton of time into declarative UI frameworks. And really, this kind of represents, I don't know, I think that we've like passed an inflection point. Declarative UI is now the way to build UI. And that's kind of cool, because I was a big part of the React community for a long time, still am, I think. And it's kind of like, hey, we were right. Like this is a really powerful way to do things. People are taking notice. And so this is a really cool time. And so I kind of want to try and play my part in that time and kind of introduce all of you to Compose and really talk about how in this environment where a big company said, hey, let's build something and invest a lot of time and energy into making it the right thing, how does that look different from React, and how does it look similar? And I think there's really a lot of interesting differences here. And so this talk is actually kind of a technical deep dive. So get prepared. Jetpack Compose has a very similar programming model to React. You'll see some slides soon. It should look fairly familiar to you. But the execution model is actually quite different. And so we're going to talk about some of those differences and what they mean. Both Compose and React kind of target functions as the fundamental building block. Function components are a thing in React, and they're actually the only thing in Compose. And so to turn a function into a component, you annotate it with a @composable annotation. And we can see here, this is Kotlin on the right. It looks pretty similar. React, actually, you pass in a props object. It's kind of one big bag of properties, whereas in Compose, we actually use the individual parameters as the properties. And so here's where things start to get interesting. If you look on the right-hand side, there's sort of an ominously missing return statement. So in React, you actually return the result of JSX, right? You return a blob of JSX. In Compose, you actually just execute other composable functions. And it kind of does the same thing. And you can kind of think of it very similarly. The two pieces of code look the same. And actually, you can kind of think that the JSX element itself is kind of like an invocation of a composable function. And we can kind of see the similarities here on both sides. Now, when we're just invoking functions, how do we kind of make it look structural? We're kind of building trees, and we want it to feel that way. And you can actually see here in Kotlin, we have these curly braces to the right of the function call. And that's actually syntax for a lambda. But the lambda in this syntax, which is called trailing lambda syntax, is implicitly passed into the function as the last parameter to that function. And so this kind of gives us this structural nesting of elements that kind of looks familiar. And so this means that if you're a composable function and you want to accept children, you would add a children parameter or any name that you want, and the type of that would be a composable lambda. And so we can see that over here would kind of be how that would work. So we're now kind of seeing some of these differences. In Compose, I actually execute these functions, whereas in React, I'm returning this data structure. And a lot of you may have heard this referred to as a virtual DOM or something. This is basically a lightweight data structure that JSX creates for you. And the equivalent in Compose isn't really there. We're not returning anything, but we do need to do a lot of the same things that React does, which is kind of handle inserts and deletes and moves and the sort of reconciliation pass. And the way we do that is we actually store things in a linear array, and that array is getting passed around by the compiler. All that is kind of done for you, and we're going to show you a little bit of that. So also, when you're building sort of these UIs, you need to introduce state at some point. And React, you can do that with a useState hook. And in Compose, you have a similar sort of concept. There's a state function, for instance, that returns a value, and you can use that as state. And you can see how these look pretty similar. You can even make it more similar if you want to, using Kotlin's destructuring syntax, but basically the programming model here is the same. So let's go into this execution model, which we're seeing now is kind of a little different. A primary sort of data structure that we use for Compose is actually called a gap buffer. If any of you have heard of a gap buffer, it's commonly used in text editors. It's a data structure that allows you to efficiently update text in the context of editing, but we actually use it for our runtime. And internally, we sort of call it a slot table, so you might hear me say that. So slot table, gap buffer, kind of the same thing. And this gap buffer represents a a sort of a linear collection of items. Underlying it is a flat array, contiguous array in memory. And here I'm just representing an empty one. And that empty part of the array is sort of considered the gap. And if I want to start inserting items into this array, I can do that and keep adding items, and the gap essentially gets smaller. I don't have those items, or I don't have those slots in the array to use. So I've inserted these items. What if I want to go back and start running code on top of that array? What I can do is if I want to keep the same item in there, I can just increment an index. If I want to update an item in there, I can change it. And then if I want to insert items, I actually first move the gap to that index, and then I can insert an item, I can insert more items, and sort of keep going. And so the point here is that essentially every array-based operation here is constant time. The only thing that is not constant time is moving the gap. And so the bet that we're making is that most UIs don't change structurally all that often. And so we won't have to move the gap all that often. And when we do, it'll kind of be good for that big insert. And so this is sort of the trade-off that we're making. So if we want to see how that looks in practice, let's take this counter component. And let's desugar the syntax a little bit. So I took away that composable annotation, and then I added these parameters to the function. And that's kind of what our compiler is doing to a real simple level. And then we're adding some calls to this synthetic composer parameter in the body of the function. And I'm going to kind of walk you through what that's doing. And you can see that also I've taken that composer parameter and I've passed it in to all of the other composable functions that I'm calling in the body. So the compiler kind of threads it through for you. But in addition to that, my compiler has added these integers. And they're just these kind of numbers. The way you should think of them is that they're sort of like a hash of the unique source position for the call site of that composable function. And so this number kind of uniquely identifies its position in the code. So when we're executing through this function, we run in the composer.start, kind of stores this group object into the array. We go and call state, and it's going to store another group into the array with 1, 2, 3. And then state itself might do something, and it's going to store this state value in the table. Then we move on to button, and it's going to create another group, and it's going to start storing these parameters. And then the actual button function itself might go and do a bunch of other stuff. But we're not going into that, but we're just going to represent it here in the bottom of the array. So we've gone through this component, and the way to look at this is that the execution of all of these functions that I'm doing sort of form an implicit hierarchy. It's like the execution graph of my entire UI. And that graph, that tree, is stored in this array, sort of as like a depth first traversal of it. But we're actually taking up a lot of room with these groups here, and it's kind of unclear why they're needed. So the groups are actually needed to deal with the shape of that graph changing over time. And in React, this is kind of what the virtual DOM is used for. It's to understand when something changes. But here, since we're a compiler, we can actually know kind of statically when one of those things is going to change and when it's not. And it turns out these groups are almost never needed. They're actually only needed for control flow. So in most cases, we just don't need to put them in there. But let's look at an example where we do need to put them in there, which is for control flow. One such example is an if statement. And so here we have a component that gets some data. If the data is null, it renders a loading like screen or something. And then if it's not null, it renders something else. So the kind of desugared version of this from the compiler is going to look something like this. And actually, each block of the if is going to have its own little group like we had before. And we see that we no longer need to pass in a key to the function. So if we go through here, we're basically going to create a group, call loading, and then we're kind of done. And that's how this sort of part of the UI is represented in the graph. If we go back and now there's data, we're going to enter in a different block of the if. And so at this point, the runtime is going to look at the integer here, the key, See, 4, 5, 6 doesn't equal 1, 2, 3. And at this point, it knows that it needs to make a change. It knows that the structure of the UI has changed. And so what we're going to do is we're going to move the gap up to the current position, and then we're essentially going to remove the group from before and start adding the new one. And this gets stored in the array like so. And so we can see that these groups are important for control flow, like for loops, if statements, stuff like that, but actually almost nowhere else. And that's pretty valuable. Now we've saved a lot of space, and we've kind of learned how to utilize this backing cache while still having arbitrary control flow. And this concept is what we call positional memoization. So this combination of using a gap buffer cache and then using the execution of kind of arbitrary code and having that backing cache threaded through, the concept positional memoization is what we came up with. And this is basically the fundamental piece of Compose. This is what Compose is built on. And so let's look at a more elementary example. Memoization, if that's an unfamiliar term for you, it's basically just a fancy word for caching the result of a function based on the inputs of the function. And so here would be a common example of where memoization might make sense. We've got an app component, we've got items and a query string, and then inside the body of our function, we're doing some computational work. In this case, we're like filtering a list based on a query and getting a refined set of results. What we can do is we can wrap that calculation with a call to this function called memo, and we're passing that in, and we're assuming that this code works basically the same way. And it does that by using this gap buffer cache that we're talking about. So when we run into memo, we store the inputs. So we store items into the cache, and we store the query parameter. These are the inputs. And since we haven't ever run this component before, we also have to run the calculation, and we're going to store the result. And then we get it back, and then we just kind of continue. But the next time we run this function, we're going to be at the same position of that array. And so we're going to go, and instead of storing items, we're going to first check to see if it matches the previous execution. And if it does, we're going to check the next one. And if that does, then we don't need to run the calculation. We can just pull out the result and throw it back. And so this memo function is kind of like a very fundamental piece for how we can start to kind of efficiently build up, maintain, and update our UI. And one of the interesting pieces of this is actually a sort of a degenerate case for memoization. Let's imagine that we took memo and we actually memoized a calculation that wasn't pure, and it wasn't really expected to be. So here we're memoizing math.random, and this actually kind of changes the semantic of the code. What happens now is that we've generated a random number, but now we're going to keep reusing that same random number each time. Each time the hierarchy sort of gets regenerated or re-rendered, if you will. If you think about it, that's kind of like persistence in a way. And so one of the big realizations that we had is that you can think of an underspecified positional memoization as equivalent to persistence. And persistence gives rise to what we all sort of call state. And so we can create this state function here just using this memo function. And actually, I'm not going to get into it, but there's a lot of other real fundamental things that you can think of that are sort of based on this primitive here. And because we're appealing to that cache, we're going to add this @composable annotation. That's sort of an indication that this function is appealing to this slot table gap buffer thing, right? And so now that this function works this way, just like a component works this way, we can do some things that are kind of cool. So hooks have this limitation right now in React where you can't use them at the root of the function. You can only use them at the root of the function. And in Compose, we can use this state thing inside of a for loop or inside of an if statement or whatever. And the reason we can do that is the same reason that we can put components inside of a for loop and an if statement and things like that. And they work very similar. And so one of the kind of things to come away with this is that a React component is kind of equivalent to a composable function, but also React's hooks are kind of equivalent to a composable function. And so the composable function is kind of a more fundamental primitive in this sense. And the interesting thing to me is that Compose overall, its execution model is actually really close to React hooks and its execution model, but pretty far from React components execution model and the reconciliation model that React has. So that's, I don't know, kind of interesting to me. But let's take this another step further. So let's imagine that we have an address component, which takes in state, city, street, stuff like that. And we're just kind of combining them into different text nodes. And then we have another component, Google, which is kind of wrapping this component with a couple of things sort of automatically passed in. Right? When we execute this with Compose, we see that the parameters are going to get stored in the slot table something like this. And so the parameters are mapped here. And then we see that actually there's sort of this redundancy. We're storing the same values again when we execute address. And so this is kind of inefficient. This is redundant information that we're storing. And so what if we didn't have to? What if, as a compiler, we could kind of get rid of this inefficiency? And so when we look at the Google component, what if we added another parameter here, which was like a bit field that we're just calling static here? And now what I could do is I could pass another value into the next composable that determines which of those parameters I know are static. And then the address component could take advantage of that information and say, okay, any of the parameters that are static of mine, I'm not going to store, I'm not going to look at, I'm not going to do anything. I don't need to. I know they're going to be the same the whole time. And so don't worry about the bitwise logic that's going on here. You don't have to write that as a user. The compiler is good at writing that. Humans aren't. So we'll take care of it. But what this allows is basically all of these redundant pieces of data that we've been storing, we can get rid of those in the slot table. And even more, there's all of these values that are left, which are essentially all of the string literal values that we had in there. And those are static too, so we can get rid of those. And so this whole thing kind of washes away to just two slots. We're just storing the number and this string concatenation. And when you start to do this, it gets kind of interesting because we say, okay, now the whole subhierarchy here is just purely determined by this one number, parameter. And so what if I generated code that looked at the number and then looked at the previous version of the number and then said, skip. If it hasn't changed, we don't need to do any of that again. And so we actually generate that code. And that code starts to look or feel a lot like what y'all might consider a should component update method. And so we do this component level skipping in a lot of places, but our compiler kind of determines what places it's safe to do so and correct to do so, and adds the code in for you. And you just write code that takes in these parameters and executes the code that you want. So here we are, Chain React 2019. I'm talking about Compose, and how does this all relate to React Native? And what are we going to do here? So Jetpack Compose is kind of going to be one of the ways to write UI on Android, and eventually React Native might want to target it. And doing so is actually kind of counterintuitively maybe a little bit difficult. React is kind of built to target an imperative UI framework, and it's not very good at targeting a declarative UI framework, even though it is one. And so one of the things I'm really interested in is how could this work? And sort of knowing the inner workings of Compose, what can we do? And I think it has to be at a more fundamental level to actually work. I think we need to really kind of think about how we can how we can form this bridge here, and maybe have these two frameworks interact, but also, how can React Native learn from this new way of doing things, and is there any sort of lessons there we can take back? Anyway, so I don't know exactly what this would look like, but I hope this talk sort of gives a good starting point. And I want to kind of leave you today just with this message that the landscape is really evolving, and this is a pretty exciting time. I think 10 years from now, we're going to kind of look back and think like, wow, wasn't it weird when like everyone started doing declarative UI at the same time, and it all happened at once, and I don't know. So anyway, I just think, embrace it, be curious, investigate how these things work. It's open source, come take a look, come talk to me, anything you want to do. There's literally engineers centuries being invested into these frameworks at both Google and Apple. It'd be a shame if we didn't collaborate, or just talk to each other. And sort of everything is the same. It's the same programming model, but everything is also different. These frameworks are being built with clean slates and with the benefit of hindsight that React didn't necessarily have. And I think it'll be really interesting to see how these models are different when they really get to maturity. Anyway, thank you.